This heavy piece of steel is the undercarriage of a KC-135R airplane. A landing gear comprises a central shaft to which an axle and wheels are attached. They begin machining the shaft. This digital lathe machines the exterior surface of the part. Sprays of water and oil cool the part, which heats up due to friction. They're now going to pierce the shaft. This drill head will remount the inside of the shaft. Alignment of the head must be perfect, so they're cautious with their work. The perforating gets underway. Turnings from the cutting are saved, and these will be sold to foundries where they'll be recycled. We see here the cutting tool used to pierce the holes in the landing gear. To perforate the part, very sharp cutting tools are used. Here, they complete an attachment hole. The hole is enlarged on its sides as required by this machine tool. The part is cooled with a mix of water and oil. Cutting is completed and the hole is now cleaned out with compressed air so that they can proceed with a visual inspection. Here, 3 pieces are rough cut at the same time by this machine. Because they'll be used in aviation, these pieces have to be machined to perfection. The machining of the shaft is now almost completed. This deburring unit polishes the machined surfaces with a compressed air tool and sandpaper discs. And now they have to verify the dimensions of the parts. This digitally controlled machine has 3 axes and does the verification with extreme precision. Here, another unit allows for the machining of parts with greater dimensions. This facility also reconditions used landing gear, such as this one from a Boeing 707. They strip off the paint with a sandblaster to verify the condition of the parts with great precision. And here are those parts stripped clean. But a visual inspection is not enough. They can detect cracks by magnetic particle concentration. They magnetize the part, and any cracks will become visible under ultraviolet light. Now it's time for the shot metal procedure, where they spray steel balls onto the metal surface to increase its resistance to fatigue. Before repainting the part, they first plate it. The part is immersed for 10 minutes in cadmium, which forms a protective coating on it that will resist corrosion. Then the part is quickly soaked in a weak concentration of chromic acid. Water, agitated by air jets, cleans away the chromic acid, and the part is rinsed with water another time. The part is now baked at 190 degrees over 23 hours to remove hydrogen induced during the plating process. Then the part is immersed in liquid nitrogen at minus 129 degrees centigrade before it's inserted in order to reduce its size. This collar is easily pushed on with a hydraulic jack. Reheating the collar makes it return to its normal size. Now the different components and the leak-proof joints are inserted into the piston. The shock absorber tube goes into the piston. This part absorbs the shock stresses when an aircraft lands. The piston is now slid into the cylinder, and they verify that the shock absorber is leak-proof. Fabrication finishes with paint baked in an oven. Some 6 to 8 months are required to make a new landing gear, and between 6 to 8 weeks to recondition a used one.
That Liebherr Aerospace switched to landing gear production, a shift that soon began to pay off. Today at Lindenberg, Liebherr produces landing gear for all the major aircraft manufacturers.
Different steps of developing a landing gear are the engineering and later on the assembly of the various components.
Meticulous work. The blank has to be dipped in a corrosion protection bath of hydrogen. Then a latest generation milling machine takes over, even to the point of automatically choosing and picking up all the tools it needs. When all that's finished, these technicians are responsible for the final assembly.
Actually, we have more than 7 projects parallel in development, the landing gear system for the C919. Therefore, we are extending our facilities in Lindenberg.
And the work has already started. Here, in 2018, Liebherr Aerospace will occupy 160,000 square meters. That's more than 1,722,000 square feet. These additional 33,000 square meters, or 355,000 square feet, will help increase manufacturing capabilities and thus deal with the rate of production imposed by its ever-increasing customers every year.
In larger aircraft, there is more than hydraulic pressure needed to hold landing gear in the up or down position. They have mechanical uplocks and downlocks. I will use this training aid to demonstrate some of these ideas. First, this represents the nose gear on an aircraft, and the position of the landing gear will hold the doors open or closed. This view is from inside the aircraft structure, looking at the nose wheel. The doors are caught on the oleo strut and close when the gear is up, and they open when the gear is extended. Here is the same thing looking at the training aid. Notice the gear position indicator in the bottom corner. This is the gear uplock mechanism. This will hold the gear in the up position even if the actuator gradually loses pressure to a bad seal. This is the downlock mechanism. It will hold the gear in the down position and make it impossible for the gear to begin retracting under the loads of landing and takeoff. Back to our large aircraft, the main gear is able to retract into the bottom of the aircraft and remain locked in place until needed again. Now a view of the uplocks. Crunchy. Here's a better view of the uplocks. In case you didn't catch that, here it is again. And here is the gear going to the down position. And again, because it is small and fast. Even the gear doors will lock into place. It would be bad if one of these decided to open mid-flight and get ripped off from aerodynamic forces. The plane even knows when to sequence opening the doors and closing the doors. All so we can have a safe flight and landing.